Good morning everyone. My name is Shiranjeevi. I am from CSC Regular. Today I will be explaining about transformer equivalent circuit. Transformers are electrical devices that transfer electrical energy between two or more circuits to electromagnetic induction. A transformer is an electrical device that transfers energy between two or more circuits through electromagnetic induction. What makes transformers so significant is their ability to change voltage levels, enabling efficient energy distribution across different applications. The operating principle. The principle of operation is based on Faraday's laws of electromagnetic induction. When an alternating current flows through primary winding, it creates a magnetic field. This magnetic field induces a voltage in secondary winding. The voltage ratio between the primary windings and secondary windings depends on the number of turns in each winding. This is what allows transformers to step voltage up or down. There's three types of transformers: step up transformers, step down transformers, and isolation transformers. Step up transformers. These transformers are used in power plants to raise voltage levels to very high levels before electricity is transmitted over long distances. High voltage reduces current, which in turn minimizes energy losses due to resistance in transmission lines. Without step up transformers, long distance energy transmission would be highly inefficient. Step down transformers. They reduce voltage to safe and usable levels, which is why they are commonly found in local distribution networks. For example, electricity delivered to the home or office is stepped down to 240 volts or lower, depending on the region. Isolation transformers. Instead of changing voltage levels, they create an electrical barrier between the circuits. This protects sensitive devices from voltage spikes, noise, and interference. They are widely used in hospitals and data centers. Application in power transmission. In a typical power grid, step up transformers raise voltage at the generating station, and step down transformers reduce it at substations for final distribution. This system ensures that power can be transmitted efficiently over long distances while maintaining the required voltage levels for end users. Critical functions of transformers is voltage regulation. They ensure that voltage levels remain stable even when the load conditions vary. Impedance matching. Transformers also play an important role in impedance matching. In electronic circuits, mismatched impedances can cause electric energy loss and reduce efficiency. Understanding equivalent circuit. An idealized representation of a transformer, simplifying electrical analysis, is the equivalent circuit. The purpose of equivalent circuit. It facilitates easier calculation of voltage, current, and impedance in transformers. Significance of equivalent circuits in analysis. Equivalent circuits simplify intricate transformer operations into manageable electrical parameters. These circuits allow engineers to forecast transformer behavior under varying load conditions effectively, essential during design and testing phases to ensure compliance with operational standards. Understanding transformer equivalent circuit. Primary impedance. ZP denotes the total impedance on the primary side, encompassing both resistance and reactance. Secondary impedance. ZS illustrates the total impedance on the secondary side, which includes the resistance and the reactance. Magnetizing reactance. XM signifies the reactance resulting from the magnetizing inductance in the transformer. Core loss resistance. RC accounts for the energy losses in the core material, mainly due to hysteresis and eddy currents. Series impedance refers to the total impedance encountered by the current in the transformer. It consists of resistance and reactance, both crucial for its performance. The total impedance is calculated Z total as the vector sum of resistance and reactance. High series impedance can lead to reduced performance and increased losses. Engineers measure series impedance to ensure transformers operate within desired parameters. Understanding series impedance is vital for designing efficient and reliable transformer systems. The series impedance affects how transformers respond under different load conditions. This is the transformer equivalent circuit. primary side has N1 windings and secondary side has N2 windings. This is the transformer equivalent circuit. Primary side has N1 windings and secondary side has N2 windings. R1 is the primary winding resistance and X1 is the leakage reactance of the primary side. Similarly, R2 and X2 are secondary winding resistance and leakage reactance of the secondary side. Magnetizing branch. It includes a parallel combination of core loss resistance, which accounts for the loss of core losses like hysteresis and eddy currents, and magnetizing reactance, which represents the energy required to establish the magnetic field inside the core. This is the transformer equivalent circuit referred to the primary side. Transformers operate on the principle of electromagnetic induction with a transformer ratio which is N2 by N1 that governs the relationship between primary and secondary windings. However, parameters like resistance, reactance, voltage, and current on the primary and secondary sides are different due to this transformation ratio. Referring the secondary parameters to the primary side allows us to work with a single circuit model, ensuring consistency and simplifying calculations. The primary side resistance and reactance remain unchanged. The magnetizing branch also remains unchanged with no change in values. The resistance of the secondary side and reactance of the secondary side are adjusted as R2 dash equals to R2 by A square, where A is the transformation ratio. Similarly, I1 is also changed. The secondary voltage and the secondary current are also changed when referred to the primary side. This is transformer equivalent circuit referred to the secondary side. In here, R2 and X2 are kept same, while R1 and X1 are referred to the secondary side as R1 dash, which is R1 into A square, and X1 dash, which is X1 into A square. Understanding transformer losses. There are mainly two types of losses, which are iron losses and copper losses. Iron losses are also called core losses. These core losses are caused by hysteresis loss and eddy current loss. Hysteresis loss depends on the material of the core, the frequency, and the peak flux density. The eddy current losses depends on the thickness of core laminations, the frequency of the current, and the resistivity of the core material. Together, these are called iron losses. Copper losses are also known as I square R losses, arise from resistances in series with windings and are directly dependent on the magnitude of load current. It is calculated as I1 square R1 plus I2 square R2. Copper losses manifest as heat in the windings, which can raise the temperature of the transformers. The total losses are the sum of iron and copper losses, significantly impacting the overall efficiency of the transformer. Understanding these losses is crucial for improving transformer efficiency and reducing operational costs. Thank you.